Hello everyone, welcome back to the precision manufacturing system. In today's video we're starting step 1 of the CPFEM and FIP workflow for magnesium alloy. This step is essential because everything that happens later during 3D microstructure reconstruction, CPFEM simulation and FIP calculation depends directly on the quality of the EBSD pre-processing. So in this video we'll go through importing EBSD data, cleaning and smoothing, grain reconstruction, orientation distribution function or ODF, IPF maps, grain size distribution, exporting Euler angles for Dream 3D. Let's get started. Before explaining this step, I need to mention I already prepared MATLAB code for this pre-processing. So my MATLAB code divided in 5 sections, so I just explain each section and you can see the code I already prepared. The workflow or the section 1, the workflow start by clearing the workspace, I mean this command, and defining the crystal symmetry for magnesium. As you can see here by this section, MTex needs crystal symmetry for each phase present in the EBSD file, and then I need to mention magnesium has a hexagonal crystal structure, as you can see here, with this value and the lattice parameters A and C. You can see this value. We find this value from MTex, so you need to install MTex and import your EBSD file and then get this information. If you don't know how to install MTex and how to get this value, please comment in this video and I will explain how to get this value and prepare this section. These values are important because they ensure MTex interprets the EBSD orientation correctly. Next, MTex plotting conventions are set so the sample axis line up properly on pole figures and IPF maps. I mean this line you need to mention in your MATLAB code to define direction of sample axis in the MTex plotting coordinate system. These settings ensure EBSD maps, pole figure and IPFs use consistent axis. So for example, this tool line ND points outward and RD points downward. Then EBSD file, we need to define EBSD file path and loaded using load EBSD by using this command. After that, then the option convert by using this file option convert Euler to a spatial reference frame, ensure that Euler angle from the EBSD system are converted into the MTex spatial frame. And here the EBSD map is by using this line, and then the EBSD map is flipped vertically. This is optional but often necessary due to how the EBSD detector defines its origin. Go forward to section 2, cleaning and grain reconstruction. The next stage is cleaning the EBSD data and reconstructing grain. First, only magnesium points are selected, as you can see by this command. Then we compute or evaluate grain for the first time using a 5-degree misorientation threshold. You can see this command. And then it's necessary for us to remove very small grains. Typically noise are removed. Here the threshold is set to 3 pixel. I mean grain is lower than 3 pixel, or it's better to say, for example, 3 diameter remove in our map. So after that, it's necessary use to MTex spline filter. MTex spline filter is used to smooth orientation and fill tiny holes in the EBSD map. This step improves grain shape and enable more accurate texture and grain aesthetics. As you can see here, you can do that by this command. After smoothing, grain are recalculate using recompute grain after smoothing by using this command. Now we go through this step 1 or section 3 that our EBSD map is green. Now our EBSD map is clean. We calculate the orientation distribution function, or ODF. The ODF describes the full texture of the sample. To match our sample coordinate system, the ODF is rotated 90 degrees around the x-axis. This is our based on our EBSD file. Maybe you don't need this section, or don't need to use, for example, 90 degree, or you can use more or less degree. It's necessary to arrange this section to convert your MTex ODF map based on your EBSD file. Then pole figures are plotted for 3 important hexagonal planes: basal, prismatic, and pyramidal. These pole figures reveal the dominant texture component in the material. MTex calc modes, you can see here, cal mode automatically identify the strongest texture peaks, which are annotated on the plot. After that, we need to set IPF orientation, coloring, and then generate IPF map in the RD, TD, and ND direction. These maps show the crystallographic orientation of each EBSD pixel using the IPF coloring scheme. For each direction, MTex maps the local orientation to an RGB color. For example, RD is X vector, TD is Y vector, and ND is Z vector. These 3 maps help visualize texture, gradients, twin bands, or local misorientation fixture. As you can see here, we by using this command, we plot IPF maps. To analyze grain size, all and section go through section 4. In section 4 we remove boundary grain and grain size distribution. To analyze grain size, all grain touching the EBSD map boundary are removed. Boundary grains are incomplete and bias the size distribution. So by this command, remove 0 entries and remove boundary grain. The remaining internal grain give a clean distribution. And another thing is so important to calculate your aspect ratios, and also equivalent diameter is calculated from the grain area, and histogram, and then histogram is plotted by using this command. You calculate equivalent diameter to understand the minimum and the maximum diameter, and then use this information for your RBE that use Dream 3D to generate your RBE. After that, a log normal distribution is fit to the grain sizes, which is typically for recrystallized or deformed magnesium alloy. By this section, you define your log normal and calculate mu and sigma. That is so important for your Dream 3D to define your distribution and determine the grain in your RBE. So both the mean and area weighted grain size are computed. This information will later, as I told already, be used to generate a realistic RV in Dream 3D. Let's go to step 5. In step 5 we export Euler angle for Dream 3D. The final step is exporting grain average Euler angles. Dream 3D expect Euler angles in bunch notation and in degree. So you can set in your Dream 3D. I will explain later. The file also record the grain size and a phase ID. You can see here I need to define. This file will be used in the next video to generate a synthetic 3D microstructure that match the EBSD texture and size distribution. This complete step 1 of the CPFEM plus FIP workflow. So you just need to follow this video and use all the command, the code, and in your work. In the next video, we'll import this result into Dream 3D and reconstruct a full 3D microstructure that match the EBSD texture. If this tutorial was helpful, don't forget to like the video and subscribe for the next step in the CPFEM plus FIP series, including CP calculation, cyclic simulation, and fatigue indicator parameter calculation. Before close this session, I need to show some figure when we run that simulation. For example, you can plot this figure when you use the code I explain. As you can see here, you can see all figure, pole figure, IPF map, and also equivalent grain diameter and relative volume fraction and histogram diagram, and then as I told already, you need to find mu and sigma. That is so important for your RV when you use Dream 3D. Thank you for watching this video.